What's happened? Cosa succede? Gessi, no, ce li ho, ce li ho. No, sa cos'è? Sono spariti i gessi, quelli colorati. I bianchi ce li ho, sono quelli colorati che non trovo più. Prima c'erano tantissimi gessi colorati, sono spariti tutti, adesso sono rimasti soltanto quelli bianchi. E ora ci sono anche quelli colorati, non solo infilati lì sotto. Ok, weak star. Now we have the reflexive. Okay. So, good morning. I hope you are here. I see 6 people, so more or less we should be okay. So I wanted just to list essentially the main things we have arrived so far. So first of all, we have this weak topology, which is the topology which makes all the linear functional continuous, is the roughest topology, the topology with less open sets. You have just the one that you need. And okay, but because of Hahn-Banach theorem, you have a lot of linear functionals. And in particular, this topology is very good for closed and convex sets because they are even, so here the closure is for the strong topology, but it's equal to the weak topology. And so we are happy in some sense that there are some good sets, which are the good sets for calculus of variation, more or less, or minimization problems, or convex analysis, and whatever, that they are still good sets when you decrease the topology. The problem is that, in general, this set, they are closed and convex, but they are not compact, and you would like to have some compactness. Well, now there is another topology which is given on the dual space, and the topology which makes all the linear functional obtained by the pre-dual set, the real dual space, to be continuous. And then the topology clearly is smaller than this one because we notice that, well, you have the embedding, the canonical embedding of E into the B dual E star star. And so you have required the continuity with respect to lower function, lower set of functionals. And you discover that, now this guy is compact for bound. The bounded sets, the bounded balls, let's say, are compact. And the only thing is that this topology in general is not as nice when you consider closed convex sets. For example, if you take hyperplanes, a closed hyperplanes, a strongly closed hyperplane, which is also weakly closed, is not weak star closed unless the hyperplane is generated by one of the vector in E. And then it's a problem to distinguish which sets are good and which are not. But finally, there is a class of space where everything is, which solves a lot of troubles, and is when essentially the weak is equal to weak star. So weak is equal to weak star is equivalent to say that E, the canonical embedding, is surjective, which is the standard definition. So the B dual is isometric, with the canonical embedding is isometric, the same as E. And now if we add these two facts, we are very happy because we discover that bounded closed sets now are weakly closed, and then are weakly star closed. On the other hand, since they are bounded, they are contained in some bounded ball. Oh, very well. So they are weakly compact. So this is the line of the theory. And then there are a lot of by-side results. So, well, you have some inverse, for example, that the unit ball so this happens if and only if it is reflexive, subset, closed subspaces of a reflexive space are reflexive, and well, you have some nice result. But this is the line that we are following. So still the thing is, there is something which disturbs a little bit. That, okay, compactness is nice, but compactness, whenever the local base is non-countable or is not generated by the metric, well, the relation between compactness and sequences is not clear, no? Because you can have a compact set with sequences which do not have any convergent subsequence, simply because you have to, well, there are some examples we will discuss this. The problem is that you have too much space, and the open sets are very large. This is more or less the idea. Okay, so now we discuss the particularly nice case, which is separable spaces. Okay, and okay, so when a metric or well, let's say a definition, so the set E is separable, is a topological space if there exists a countable family dense set. Okay, this is almost an exercise, so they present as a proposition, so I prefer to give you as an exercise. So let's try to do that, or you try to do that. If E is separable, F is contained in E, then F is separable. So well, it's not with the same sequence, you have another sequence, but still it's okay.
Professor?
Yep.
I think this statement is not true in general. If A is separable and metric space, then we can prove F also separable.
Yeah, sorry, yes. I always forget that we are working in balance, yes, separable metric. Yeah, because you need to use the bolts. I always forget. So we are working with Banach spaces, and then it is the metric is that one. I'm sorry. Okay, so now the first theorem. So if E star, okay, let me say, okay, yes. If E star is separable, then E is separable. So the converse is not true. And okay, this is why I get confused, because I'm not specifying E is always a Banach or at least normed space, so it is metric, and that's okay. The converse is not true. In general, because the example is that we will see the dual of L1 is L infinity, and this one is separable. So the one of, let's see, in Rn, just to fix the thing, otherwise, and this one is not. Okay, proof. All these proofs, they rely in some sense to the Hahn-Banach theorem. So they say that you have a lot of linear functions in E star, and they do whatever you want them to do. And so the implication is something that, well, if you will choose some vectors here, countably many vectors, and all these vectors will see all the vectors in E star, all the countable base in E star. And then, well, there cannot be other vectors in some sense, because otherwise you will have a linear functional which is not in the closure of the other linear function. Okay, this is just the explanation, but let's see how to do that. So let Fn is the countable dense set in E star. Okay, so now we know that by definition there exists Xn in E such that, well, Fn applied to Xn is, here I choose greater or equal than 1/2 norm of Fn. Well, simply because the norm is the supremum among, so this is the definition of the norm. So the supremum of this guy exactly among all x, there is this number, and so there exists at least one which satisfies this. Okay, so let L is the set Q, let's say sum I equal to 1 to n for every n of Qi, Xni, and Qi are rational. So this is the linear, she should be the linear span of the set Xn, but not over R or over C, but only over the rational number. This is because this set is countable. Clearly, its closure contains, so what is its closure? The closure of L is what? Is the closure of the linear span of the Xn. So it is a closed subspace of E. And this closed subspace is clearly separable by construction. Now, the contradiction is if it is not the whole E. If, let's say, the closure of L is contained but not equal to E, okay, then there exists well, you see now where we are going, no? We are heading to take a point outside, and then take a functional which separates, which is 0 there, but not 0 everywhere. So there exists a functional f in the dual with the properties that f over the closure of L is equal to 0, but norm of f, well, we can choose, for example, is equal to 1. On the other hand, let's go back. This Fn is dense in E star. So there exists Fnk converging to F. And then what we have? So from here you have an x0. So here it means that there exists x0. Fx0 is, well, greater than 1/2. Doesn't matter. But now we have that Fn at x0, which is equal to 0, because by my assumption,
Fnk maybe.
oh, wait a minute. Wait, I missed the argument now. So that converges strongly. So for any wait, I'm missing the. Just the argument, and it is a stupid argument now, but I'm now, so F and K converge to I'm sorry, I cannot conclude, but it's already concluded here, and I don't see why I cannot handle it. F equals, I'm sorry, I don't see the end, but the end is already here, because I get the contradiction that should be F, on the other hand, should be F on x0 equal to 0. I don't see it why, and it's because of this convergence, or the distance. Ah, yes, it's so stupid. So f of L is equal to 0. Yes, okay. And then what happened now that for all x belonging to L bar, because of this convergence, I was confused by T as 0, it doesn't matter. Because of this convergence, what I get? Fn k of x converge, so converge to 0. Because the limit, this converges to fx, which is equal to 0 for each x in the closed set. Okay?
Yes. space. Okay.
And okay, so now the conclusion is the following. Now take, so, but also f and k, x and k, and I forgot to say that x I can take equal to 1, f and k. Okay, this is less or equal than, since this norm is 1, is the norm f and k minus f. This is why one has to write the notes a little bit better. Okay, so this holds because the norm of x and k is less than 1, or 1, doesn't matter. Okay? On the other hand, this guy is equal to 0. But this guy is greater or equal than 1/2 the norm of f and k. So I deduce that the norm of f and k converges to 0. This is the only way to make this inequality hold, because this goes to 0, this goes to 0, and this is greater or equal than 1/2. So the only way is that n k converges to 0. And this implies, by this convergence, that norm of f is equal to 0. So f is equal to 0. And now if you recall by Banach, so a way to say that a subspace is dense is to say that every linear functional which is 0 on the linear space is 0, which is exactly what we proved. So by Banach, L bar is equal to E. I'm sorry, it was so stupid, I get confused. Corollary, which is now we are in the good part. So E separable reflexive E star separable reflexive. Okay, what with the easy implication is, well, what we have proved last time. So the theorem above plus, we have already the implication that E star reflexive E reflexive. Okay? And if you remember, we have seen last time, this was essentially because being the closed ball in the B-dual, let's say, the weak and the weak star topology in the B-dual space the same, and knowing that the closure of the unit ball is the weak star topology, the image of a unit ball is the unit ball in the E star in E star star, then we deduce that the equality, so the subjectivity of the canonical map. Okay, now this gives that separable means separable, reflexive means reflexive. So gives this implication. Now what about the other implication? Well, the other implication is the same because you deduce from E star star. Okay, E star star, you know that from E star star, so E star, pardon? So E star star is separable and reflexive. Because if E is separable and reflexive, E star star is just, let's say, there is any, well, it's just a relabeling of E in some sense, because it's the canonical embedding is a surjection. And then you deduce that the pre-dual of E star star, which is E star, is separable and reflexive. Okay? Okay, now we come to the important fact here. So, E separable. So essentially, then the unit ball in E star with the weak star topology. So let's say the topology sigma E star inherited from E. Okay, here I can take also the closure, doesn't matter, is metrizable, and vice versa. Which means that if the unit ball with the weak star topology is a topology which is generated by a metric, then E is separable. So this is, I should say, well, this and the statement regarding the weak topology on E is the corner of this chapter, because at this point we can conclude this, the picture here, saying that if I add separability, so what I deduce is that the bounded sets are metrizable. You can put a metric over here, which gives you the weak topology, and you are happy. In some sense, it is the best. So you have a compact set with a metric over it. So let's do the proof of this guy now. Okay, so the assumption is that we have the separability, so we can take xn countable dense in the unit ball of E. Okay. So now I define, but okay, let's do as a, because I don't know how to make you feel why I do some steps. So essentially, I want to say the following. So in picture, let's say, let me put a picture here. So let's say this is the ball in E star. Okay. And now my open sets are, well, you assign essentially some F with some X, and this is the ball Fx minus, okay, some value alpha is less than epsilon. Is the picture we had last time. Okay, so this is the value, the closed hyperplane Fx equal to alpha, and then, okay, I put the size epsilon here. And now what I observe? Well, first of all, it's clear that I can choose x norm of x equal to 1, no? Because, well, I just scale alpha and epsilon. Now I cannot pick one of those, one general x. So let's say that you are just forced to take this xn. So you're just forced to use the functions fxn. So this f maps to fxn. Which means that my slope is slightly different here. But it's clear that if the two slopes, so the angle is not too large, and since I'm living in a bounded set, well, I can just squeeze a little bit my close, let's say, neighborhood of the hyperplane, and the orange stuff will be inside my neighborhood above. So, in some sense, the idea is that, well, all this set of functions they control the function fx. In the sense that if I know that these sets are small, certainly this guy is small. And this is the inclusion. Okay, now is a general fact that if I have countably many objects like this one, which are called semi-norm, or semi-distances, but this is semi-norm, then the following object is a distance. So the sum this is a pretty general fact. So the hidden part that is not written in the notes is this observation. It's not written in the book because you give the distance that you do the estimate. But this is the hidden fact. And then the rest is just a technique, in the sense that you know that these objects here are what is called semi-norms, and you have countably many, and the countably many, they control all functionals in bounded sets, in this sense that this functional, if you want this to be small, it's enough that all the Gn are small, or enough many are small. And then there are not only this one, other formulations, for example, can be the max, it can be whatever you, one divided by the other, doesn't matter. The important thing is that an object like this one becomes a distance, and with this observation that the control of these quantities, which is here, they control the quantity they wanted to control, well, is the fact that tells you that this distance will generate the topology. Okay, so this is a comment that I prefer to do now. Okay, because the rest is just distance. So I want to show that, okay, that it is the distance is left to you. Actually, it is more than a distance, it's a norm. So D is a norm. This is by just that subadditivity, linearity is because it's the sum of objects which are called semi-norms. And the fact that when it is 0 is because xn is dense, and when xn is dense, it means that the functional is 0. This is by exercise, I leave to you. So now what I want to prove is that the topology generated by the norm is equivalent in some sense to that guy. So what is the easy part for you? Is easy. So I want to prove that the topology, let's say, that for all V weak star neighborhood, okay, there exists, and then let's say, of, let's say, f bar, there exists a ball with respect to the distance d of f bar and a radius r, such that the ball is contained in V, and this implies what? That the topology generated by D is finer, and on the other hand, and the opposite. Which implies that the topology is rougher, and then both together implies the topology is the same. Okay. So now let's discuss about the easy part. The easy is the opposite. So let me cancel. I think we don't need this. So if, well, first of all, first observation, I can take f bar equal to 0. Because you observe by the representation, well, there is no much difference here, no? I mean, this is translation invariant, and the definition of of a weak neighborhood is translation invariant. So I take f equal to 0, and so now I want to choose, let, let's say G, or let's say let f such that the distance of f from 0 is less than epsilon, and this is equal to the f such that the sum 1 over 2n f xn less than epsilon. Well, now, hence, there exists a k sufficiently large, let's say capital N, such that, okay, now, the norm of f is less or equal than 1, and xn is less or equal than 1. So this object here is less or equal than 1. So I require the sum from n to n plus 1 to plus infinity of 2 to the minus n is less than epsilon half. And now I require set V hold f such that, well, now the rest of the sum is small, so let's say I ask that for each n from 1 to capital N, it holds f xn less than epsilon half. Okay. So let's see if this guy here is inside this guy. Well, it's just the sum, now you see. Because I have the sum for each f inside here, 2 to the minus n. Okay, this is less or equal, then I sum up to n this guy, which is 2 to the minus n epsilon half, plus, well, I sum now the rest, which is 1. I replace instead of epsilon 1, because this cannot be larger than 1. And then you discover by definition this is less than epsilon 1. The sum of this guy is 1, so it's less than epsilon. So essentially, the idea is that each ball constructed with this topology, this metric, well, contains a linear subspace which is generated by the first capital N components of your metric. So now let's do the opposite. The opposite is the drawing that I'm going to do here, which means that there exists, well, since this takes all, well, a dense set, at some point there will be some linear combination which is very close to my x. Let's do now the opposite. Okay, let me see if I write something of this exactly this. now we do, okay, use the inequality. So I have to estimate this guy from some x0 fixed, or let's say x, and I write is equal to f x minus 1 over the xn, which is one of my sets, plus f xn less or equal. Okay, and now I observe that by the norms, this is less or equal than 1, and this plays the role that you see. I can switch a little bit the interval, and I'm still close, because it's not unbounded. My set is not is bound. What is less or equal than x minus xn plus, okay, this guy over here. But this guy over here, let's go to the distance here. Certainly the distance is larger than 2 to the n that guy. So of f from 0. Now the thing is done, because choose, so is the opposite of what you have done here. Choose xn such that norm x minus xn less than epsilon half, and the radius of the ball, so it is the f from 0 of radius of, yes, and then choose the radius of the ball, which is less than 2 to the minus n epsilon half. So now we conclude that for all points here, this is less than epsilon half, this guy is less than 2 to the minus n epsilon half, then 2 to the n, then this guy is less than epsilon. So I conclude that the two topologies are equivalent. Let's see the opposite. So assume now the ball in the duals with the weak start topology is can be metrized. Okay, so it means what? It means that, so let's take just the ball in 0. So this means what? It means that the set U such that f whose distance from 0 is less than 1 over n. So this is an open ball around 0, should be open in the weak start topology, which means it contains, well, some open neighborhood, which are all the f, such that, well, I have counted many points. So it's f, xn, okay, this is k, less than some, well, here I can choose less than epsilon, doesn't matter. And from k equal to 1 to some capital K, which depends on n. So for each n, there exist finitely many points, which determines a neighborhood in the weak start topology, determines a neighborhood V in the weak start topology, and since this is open, this set should be contained in that guy. So I found okay, the countable set of points. Okay, I can require even them to be And now what I do, any suggestion here, because it's exactly what we did last time. So I take the linear span, which is still separable, and its closure. So I want to say is the closure of the span of x and k, which is separable. What we have proved with the first theorem, more or less, was inside the proof. Okay, so let's assume that this is not the case. So let now, so it's not the case that is the full set. Let's now f bar such that f bar on L is equal to 0, which means that f bar on all x and k is equal to 0. If I go back here, it means that f bar belongs to un, let's say un here, I have 1 over n, un for all n, because being 0, it is inside all the neighborhood that I chosen. But if it is inside un, then f bar should be only equal to 0, because it's a metric space, and the intersection of this ball is, well, the metric space is separates points, and in particular it implies that the only point inside all the balls around 0 is just 0. And now again, by Hahn-Banach, you see it's the same we had last time. By Hahn-Banach, L bar, so L is equal to E. So the arguments are more or less the same. Okay, so let's do now, I don't know if to do the dual statement, because the dual statement is more or less the same. And I want to finish this thing. So let me see. Let's see just the variation. So the dual statement is the one about E star. So let E star separable, and then the ball in E with the weak topology is metrizable, and vice versa. So E is always Banach for us. Okay, so okay, so there is one part which is very similar, so we just sketch the proof. So the thing is the same where you just replace the distance with the other distance. So the distance, so if E star is separable, let's say if E star is separable, then your new distance is xy, or x minus y is the sum to the n, and this is fn x minus y, where fn is the dense set in the ball, the unit ball in E star. And you repeat the proof, the inequalities are just the same. You switch instead of f, fn, and so you get immediately that this guy is contained in your set. So now for the other part, it seems to me that This is a little bit long. I forgot when I prepared the lecture some days ago. And I forgot. First do the same step. So because the other part now is similar, you construct the sequence of, okay, so this y implies this gap, this part, sorry. So this implies that the topology, I have to say that this topology is wait a minute, there was one point, the one was the same, sorry, is this one? Well, I don't remember. I remember it was more or less the same. There was just one difference. I don't remember now what is the difference. And I wrote the sentence. And okay, I don't know what to say. It's more. What the same step. So you construct the neighborhood. So now suppose that is matrix. Okay. For the other part. So again, you repeat and then you construct the sequence of dense set like here for the converse. So and now these are F and K. Sorry, I want to be fast because it is exactly the same. There was just one point. Now, if not either exists a dual. Yeah, because now you go to the dual, and this is 0 for all F in the set. Okay, so the proof is the same. The only thing you have to use, once you construct this family here, so for the opposite, so okay, this fact is the same. For the opposite, you construct the family F and K, which generates the weak topology on the ball. And now the difference is that if you take, so here, when you take L, which is the closure, here is the difference. Okay, you cannot use Han-Banach, because Han-Banach tells you, well, there could be xi, which belongs on E star star, minus the j of E, such that separating L, different, so what happened? This separates the L from E star. Because before we know that all the things are inside, are by Han-Banach, are in the dual, but here, I mean, this is a closed hyperspace, subspace, and then you can have a point in the B dual. Because it's not like here that I'm taking, I need to say that the point is in the dual, not like here one. So being 0 here doesn't mean that it is 0. So there exists a point, and xi on L is equal to 0. But xi is not 1. So this may happen. So, but what we use here, just I'm going a little bit fast because this is the new argument. So what I'm using here, in order to conclude, I'm using that J of the ball weak star is closed. So is dense. So there exists xn such that J of Xn converge weakly star to Xi. And now you get the contradiction, because it was the inequality we had before. Because this guy is 0, but on the other hand, these guys, they cannot be 0, because their norma should be 1, for example. And so I get the contradiction that, so here the contradiction is that the Hahn-Banach theorem. There the contradiction is the fact that the topology is the weak star topology. Okay, so I'm a little bit fast. We can skip. I don't consider this is really instructive. Oh, so we arrive finally to the important corollary. That was the important part, I want to say. So if E is separable, Fn contained in E star bounded, then there exists Fnk weakly converges to some F. This is the important statement. So the proof, well, the proof is immediate now because we know that F and K, weakly star converge. F and K is contained in some ball of some radius R, and this is closed, and it is compact actually, weakly star compact, and this is our theorem, no? We had last time. So the balls in the dual space are weakly star compact. On the other hand, we know that weak star topology is metric, and is the theorem that not the theorem where you have E separable implies that the dual ball is metric with a weak star topology. And now in a compact metric space, there exists a subsequence which converges to F. And let me add one other thing, is that well, I think, so let's, if E reflexive, okay, let's add his remark and that's it, is an exercise. If E reflexive, Xn is a sequence bounded in E, then there exists a subsequence weakly converging to some X. But I'm not saying that E is separable. But the trick inside this exercise, I think in the book is done as a statement, is that the linear span generated by N, the closure of the linear span, is a separable reflexive Banach space. Hence, the dual is separable reflexive Banach space, because I have the previous corollary that reflexive separable implies reflexive separable. And then I apply the corollary here. Okay, this is just an exercise. So now let's go on. And well, this is a nice criteria to have the reflexivity. So it's uniformly convex space. It's nice because many spaces are uniformly convex. For example, Hilbert spaces, and so this is the last chapter. No, I want to add another thing. Uniformly convex spaces. So what does it mean uniformly convex? Okay, the picture is quite clear, no? So if this is the unit ball, and if I take 2 points in the ball, the distance of the middle point from the border is uniformly larger compared to the space. So there exists for, let's say, if the middle point is, so let's say, if the distance is larger than some quantity, then I'm sure that the middle point is larger than some point. So in, roughly speaking, if norm of x, norm of y is equal to 1, norm of x plus y, so I write like this, epsilon here, is less than 1 minus epsilon, then x minus y is larger than some delta. For all epsilon, there exists a delta. So, and this is the opposite implication is clearly that if these guys, wait a minute, I reverse the implication perhaps. It's the reverse implication, I'm sorry. Indeed, because I want to read in the, gosh, today is not my day. For all delta, for all epsilon, for all epsilon, sorry, for all epsilon, there exists a delta. Okay, this is the implication. So the implication, the opposite implication is that if the middle point is very close to the border, then they should be close. Okay, I'm sorry. I inverted the implication. So theorem here is the following: uniformly convex Banach spaces are reflexive. Which is surprising. Well, it's not surprising because at the end you see in the proof how it works, but essentially you have a geometric information which gives rise to topological information, because reflexivity is a topological information. And however, there is no clear inverse to this theorem, because you may have a reflexive space with no uniformly convex norm, and vice versa, you have spaces which are not uniformly convex. Actually, the unit ball is not even convex, but they are reflexive. Okay, so let's see the proof. I don't know if to give the proof. Let's see by time. Yes, okay, let's do the proof. And, so what I have to prove. So in my knowledge, I know that the embedding of J E is dense in E star. Star. This is what I want to prove. And there is no discussion about the density in which sense. Well, it can be the density in the weak and in the strong topology, but not in the weak star topology, because the other is for free. Okay, so which means that for all xi in the unit ball, here we take the unit ball, radius 1, even close doesn't matter, there exists x in the unit ball of E such that the norm of xi minus the embedding in E star, in this norm, is less than epsilon. So for all, if I fix xi and I fix epsilon, I have to find a point which is very close. For epsilon, xi, there exists a point which is very close. So now what I want to use, so essentially I want to find that you have, you have points which are, should be far apart, but instead they are very close because of the uniformly convex assumption, which implies that if you know that this guy is large, very close to 1, then they are very close. So this is the implication. And then I will show that, so the proof you get a contradiction because if it is not dense, you have a ball which is separating, but on the other hand, you have certainly, in the weak star topology, you have points. So you use the, well, let's see the argument. So take F in the dual such that, well, psi F is larger than 1 minus delta half. And the norm of F is equal to 1. So the existence, well, you have certainly, because the norm of psi is equal to 1, is less or equal than 1, or let's say norm of psi is equal to 1, or let's say norm of psi is equal to 1, it's the same, I can assume, no? Because by scaling, I can assume that norm of psi is equal to 1. And certainly, by definition of norm, there is an F such that its evaluation is close to 1 as much as I can. So define V are all the set eta, the points in E star star. So this is a neighborhood of my psi, a weak star neighborhood. Eta minus psi F is less than delta half. This is a weak star neighborhood. So essentially, this ball, I put a point, I take a point here. I want to say that there exists an X. Well, for sure, I take 1/2, which is almost, gives almost the value, and then I take a weak star neighborhood V. Okay? Since you remembered that J of E star closed, weak star closure is equal to E star star, then there exists an X such that J of X belongs to V. So I have a point inside here, which is my X. Okay, on the other hand, I assume that this does not hold, so there exists an epsilon. So psi, the distance from psi from, let's say, J of X, because my assumption is that this does not hold, so there exists an epsilon such that the distance is greater than that quantity, which implies that psi plus the unit ball in E star star of radius epsilon closure does not belong to J of E. So this is, the proof is a little bit involved, I'm sorry. So essentially, there exists so I'm for sure there exists a ball here which does not contain the all the image, in particular this point X. Or vice versa, or again, X plus the J of X plus the ball plus this ball does not contain psi. So the two things together implies that you have another neighborhood. So this implies that there exists another neighborhood, weak star neighborhood, containing psi, but not J of X plus the ball of radius epsilon. Because my theorem was that this ball is weak star-star compact. Is weak star compact, and hence it is this guy here is a closed set. I don't have a point, so there exists another neighborhood separating it. Okay. So now you see where the argument is going, because what I have that when I pick another y inside here, so pick y in E such that y belongs to what? So belongs to the V and belongs to W. And is in the, sorry, let's say J of Y, J of E. But if we go back to the norm, remember that it is an isometry. Norm X minus Y is greater than epsilon, because it is in the second neighborhood. But on the other hand, the distance, the neighborhood does not belong to this closed compact set. Okay, and now we are done. So I have a point whose distance is greater than 1, but they belong to the first neighborhood. So I have that f x minus psi f is less than delta half, and the same for y, because they belong all to V. So let's compute now. Now from this guy, what I get? So I have 2 psi f is less or equal than, okay, here I add delta plus f of x plus y, which is less or equal, remembering that I assume f is equal to 1, is delta plus x plus y. Now, this guy is 1 minus delta, so what I obtain, x plus y greater or equal, so it's 2 minus 2 delta. Now let's go back to the condition. So here I have that, okay, x plus y is as close as 1 as I want, but on the other hand, the distance is uniformly far. So this contradicts the uniformly convex. Okay, so let me repeat the proof. There are several arguments, but the basic idea is that the property of being non-dense, it means that you have a ball. So you can find points, the sequence which weakly converge is a sequence which is a uniformly distant. You can build a sequence which is uniformly distant. On the other hand, however, from the point of view of linear functional, they should be uniformly closed. So they should converge. And both together implies that their norm should converge to 1, but on the other hand, being a uniformly distant, they cannot converge. So you have this contradiction because for xi, the f xi will converge to 1, to the norm of xi. On the other hand, for x plus y, this cannot converge to 1 if it is uniformly convex, because all these points are at uniform distance here. So this is the contradiction. Not the smarter way I presented it, so the last two results here are something important. Well, the first is not, so it's just almost an exercise. But it's very useful, however. If E is uniformly convex, I'm sorry, Xn weakly converges to X, and norm of X is greater or equal than the lim sup of Xn. Well, we know that this is less or equal than the lim inf, which implies that it is the limit of the norm. Then, actually, Xn minus X tends to 0. So you have strong convergence. So why is that so? Well, it's always the same trick. So I want to use the other implication, no? That x plus y should be large, then implies their difference is small. But the only thing is that here I have norm 1, so I just rescale everything. Okay, see, if norm of x is equal to 0, there is nothing to prove. So assume that, let's say I divide by quantities greater than 0. If the quantities are 0, then when you say if these quantities are 0, the limit is trivial, being 0. So set yn xn over norm of xn, y x over norm of x. So both have norm 1. And from this observation, since from this guy plus norm of x less or equal than lim inf greater or equal than lim sup, which is the assumption. So norm of x is the limit. You deduce that yn will converge to y. Because is with the product of some constant which converge. And then the norm of y is less or equal than the lim inf. Okay, I say yn, but actually also yn plus y divided by 2. But then this is equal to 1. So I get that yn plus y half tends to 1. And the implication of uniform convexity means that yn minus y tends to 0. And this is the proof. Last result for this lecture and this thing. This is not in the book, but I consider very important, which is the Krein-Milman theorem. So the Krein-Milman theorem is in some sense strong, well, it's not necessary, but it's related, let's say, to our Mazur lemma, which, if you remember, it tells you that if you have a weakly convergent sequence, okay, then there exists a sequence of linear combination which converge strongly. Okay? So the Krein-Milman is so something related to this fact when instead of, well, the sequence is not a sequence, but are just extremal points. So I have to say the definition of what is an extremal set. So K contained in E is convex, and Sk is extremal if for all x, y, if, okay, let's say x, y belonging to K, 1 minus t, x plus t, y belonging to S with
Implied x and y belongs to S.
Pardon?
These points also belongs to S. X and y belongs to S.
I take this.
Extremal point, set of extremal points.
Because what you say, if these are in S and these are in S, it's just convex. Not that is extremal. Extremal is, so okay, a point here cannot belong, if this point is in S, the only extremal set is K. This point here is, this is an extremal set, this is an extremal set, and the whole set is an extremal set. So the implication is that if one of the points in between, one point in between is contained in the set, then it contains the two set, the whole segment. So this is the extrema. Because otherwise, I don't know what you want to say.
No. Cannot expressed as a convex combination. Non-trivial convex combination cannot be expressed. The points in extremal points cannot be expressed as a convex combination like this.
The extremal point are just in the following sense are points which cannot be written as extremal combination. It's implied by this guy, because if it is written as a convex combination of 2 points, the 2 points should belong to the extremal point, so they should coincide with the point. This is for sets, not for points. Okay. So if x in extremal point are just the fact are when S is just 1 point. And now let's take the theorem. So if K contained in E, or, well, the theorem it works also in E star. I just state in E because it's simple, but is okay, it's compact, convex compact. And now convex compact, it's in a whole topology you can say. So it can be E or E star, and here I can use the strong, weak star. Then EK is equal to the closure in the suitable topology you're using of the convex combination of the extremal points. So you see, in Mazur we say more or less the same. No, it is in the closure of the convex combination, and here is the closure of the convex combination of particular points, which are the extremal points. Okay, what about the proof? And okay, we have to choose a setting. I choose the E with the weak topology, because it's the nicest one in some sense. For reflexive space, it's the one that have compact set. Otherwise, it's difficult to say which set has compact. So, proof. But I think in the proof doesn't matter what you say. So you define, okay, in order to get extremal points, how to build them? Well, in finite dimensional space is very easy, because you take linear functionals, and then after you maximize one linear functional, and then either you get immediately an extremal point, or you get an extremal face, and then on that face you minimize a different linear functional, and then you get finally, after finitely many iterations, you get all the extremal points. So here is like more complicated, and so the proof. So you define the family S contained in K, which are extrema. So clearly S extrema are convex by definition, no? Because if you have 2 points, then the value in between should belong to S. Otherwise, you get a contradiction. So S is extremal and convex. Let me take this. No, the definition is not written, but it's better to write like this. Okay, so the properties. So P is not empty because K is contained in P. By definition, K is convex, and it contains all the points. So there is the conditional is empty for this case. If A is A alpha, let's say, is a family, A alpha is a family in P, then the intersection is in P. And here you check just the definition. You have a point which is represented by 2 points in this guy, then, well, okay, all these 2 points should belong all the A alpha, so it's just directly. And finally, if F is linear functional, then the set of points such that Fx is equal to the maximum of Fy for y in K, this is extrema. And okay, the last remark is the remark I made here that, well, in one-dimensional case, to find extremal subset of a given set is just you can maximize a linear function. This is this step over here. So now what you do, so now we apply Zorn lemma, because order by inclusion, and let, okay, A alpha be a maximally ordered subfamily. So I'm using here, as in the Hahn-Banach theorem, the inclusion with respect to the sets. Here I don't have anything to extend, it's just sets. So let S A alpha, which belongs to P. So now let's observe this guy. So if S is not a point, so for example, there exists X and Y belonging to S, with X different than Y, then there exists an F in the dual separating X and Y. And so I get a contradiction, because now there's a contradiction. So I take one of this set here, the set X in S, such that F, okay, for this F bar, let's say F bar Y X is equal to the max over Y in S F bar Y is an extremal subset of S and strictly closed. Strictly contained, which contradicts that I found a maximally ordered family. So I can still add one. So conclusion. My conclusion is that the intersection, so all let's say maximally ordered subsets. Okay, sorry, conclusion is all extremal subsets of K contains an extremal point. Okay? Because I just repeat the construction and I prove that K contains an extremal point, but also any S. So how to conclude finally that all the set of extremal point is, dense, so all the convex combination is dense in K. In particular, if, let's say, the convex of the extremal closure is contained but not equal to K, then is the same. There exists by Hahn-Banach F bar separating, okay, this is, let's say, L from K, from a point in K, or from a set in K, and then I have another empty set here. So I can construct another extremal point. Extremal point, which is a contradiction because I already imagined to have taken them all. So conclusion of the thing is that for any extremal subset, I found the point, and the set of points is contained in K simply because particularly nice extremal subsets are sets where I get the maximum among a linear function, like in the one-dimensional case. Okay, and then there is also another improvement of the result when you take, instead of a, well, you can represent each point like the integral of a measure on the extremal points, which will not discuss it. Okay, I'm sorry I was late today. I wanted to finish this part here, and that's it. So I'm sending, I have address of 3 of you. I will decide which exercise are nice, and I'm sending the list. And if there are no questions, see you on Monday at 11.
Thank you, Professor.